Okay, now that we've covered wind and all the different motions, air particles and how they change, we're going to just take an average circulation. If you were to average the circulation around the world and just look at it, not the little tweaks of a low moving by West Virginia or somewhere in the United States, just look at it as if you had seen it over the whole year, and this is what it looked like. That's what we're going to look at today. There's some things to be gained by that, to understand why we have certain weather in the mid-latitudes, or why the poles are different, or why the equator is a whole different tropical atmosphere. So what are some of these? What are some of the things that we've learned about? Well, let's look at it if we had a non-rotating Earth. Guess what? Mercury is kind of this way in our solar system. I was just reading a Star Trek book, or a Star Wars book actually, and they had a planet they went to that did not rotate, and the only habitable part was right on the edge of the sunlit surface and the dark side. So you can see it here. If you have that on the dark side, the air is going to get really cold. On the light side, the air is going to get quite warm and hot. So the air is going to tend to rise where the sun's the strongest. It's going to tend to sink on the other side. So what you wind up with is just a big circulation of air going from one side to the other. Because the atmosphere, no matter what, is still trying to get rid of one side being hot and one side being cold. In the Earth, we have it rotating. So the Earth rotates, the sun moves up and down because the Earth is tilted as it goes around. So all that impacts, and what do we wind up with? We wind up with different pressure zones around the globe. If you look at it, winds converge towards the equator, and they diverge around 30 degrees north. Well, where winds diverge at the surface, we tend to have high pressure. Oh yeah, up towards 60 degrees north, we tend to have low pressure at the surface. So you actually pick out that along the equator, there tends to be lower pressure. Along 30 degrees north, you tend to have higher pressures. You get up near 60 degrees, you got lots of low pressures moving by. And up over the poles, there many times at the surface, there tends to be high pressure, but there tends to be low pressure aloft there. And you can see that. Here we talk about it a little bit. And actually, when you look at it, this is just an average pressure pattern. Low, low, low over here somewhere, around 60 degrees north, high pressure right across here around 30 degrees north. And yes, these move up to the north in the summertime and down to the south in the wintertime. Oh yeah, there's going to be an intertropical convergence zone across around here somewhere that's going to be right around the equator. You can see a little low pressure there, a little low pressure there, a little low pressure there. So it looks very much like what it should look like. So around 30 degrees north, we have these high pressure systems. Used to be when the sailing ships went into these areas, they called them the doldrums because they couldn't move. There was no wind across this big part of the ocean. Now, the south side of it, you would have easterly winds moving you from Europe over to the United States. North side of it, you could move back from the United States over to Europe. But in between, if you got into the doldrums, you weren't moving and you could spend days there. There's some interesting things about these highs, too. They influence what type of weather is along either the eastern side of the high or the western side of the high. Take a look at the high that's over our Atlantic Ocean. If you were to look on the eastern side of the high, the Sahara Desert's over there. Well, why the heck would it be on that side? Well, you get warming, you get lower relative humidity, fair skies typically. You don't have much in the way of moisture there. On the other side, over, say, towards Charleston, South Carolina, or the Outer Banks of North Carolina, you get lots of moisture coming up from the tropics, wind up with lots of instability and lots of showers and thunderstorms, particularly. They can be very impactful during the summertime. guess what? There's another area. One of the driest deserts in the world is around on the Chile as it faces the Pacific Ocean. And that desert is also rather cloudy because it gets some influence from the ocean. But it doesn't ever get any rain because the lower levels are so dry. There are some poles. Up in the towards the poles, we have areas of low pressure that circulate. The Icelandic low of the United there's an Aleutian low. In southern hemisphere, there's almost a continuous belt because you don't have the land masses interrupting it. And between them, you have the polar fronts right in there as well. And across the top of the world, you have the polar vortex. It's a very strong circulation sometimes, just sitting there. And in between where we live in the mid-latitudes, you wind up with this wavy pattern. So sometimes if the waves are coming out, if you're on the west side of a low, for example, you have winds coming out of the northwest. Well, we know to the north of us is Canada, which is much colder than our country. And up north of that, it's the North Pole. And you wind up bringing colder air down. Oh yeah, on the east side of that same low, you're going to bring warmer air up. And depending on how strong these are, how much cold air is going to come down and how much warm air is going to go up ahead of it. When you look at the tropopause, we've been talking about the tropopause a lot in this course. The very first week of the course, we talked, well, why is tropopause higher down over the tropics? We learned that density had a big impact on it. The air moved apart. Well, if you look at the tropopause, you'll see over the tropics, yes, very quite warm, tropopause is fairly high. Over the pole, air is consistently cold, tropopause is quite low. However, between the two, the tropopause can go up and down depending on fronts. So you may have the tropopause fairly low. When a very strong cold front went through, you're pushing the tropopause down towards the earth, especially with low pressure there. And then the other token, when you have warm, higher pressure coming from the south, pushing upwards, tropopause will go back upwards. So it's an interesting mix in the tropopause over our area because it can go very low and it can go very high, depending on the temperatures and the pattern. There's a trade wind inversion. Trade winds are that easterly flow along the south side of these 30-degree north highs. And as part of that, sometimes the ocean can be kind of cool there. So you may have low SSTs. The layer is relatively cool, humid because it's over the ocean, right? But above it, there's warming because it's part of the descending branch of this Hadley cell that we talked about before. Intertropical convergence zone fluctuates greatly over land. Notice over Africa and Asia, the intertropical convergence zone in January, well south, way out of India. In summertime, well north, even changes over Saudi Arabia area in the peninsula, Sinai Peninsula. So why is that? Well, we know the sun really heats land up a whole lot more than it does the oceans. So it allows over land to move the intertropical convergence zone to where the hotter air is over the land. So it'll move north in the summertime and south in the wintertime. Now, if you look at the Atlantic Ocean, you'll see it doesn't really vary a whole lot. Oceans take a lot of heat to warm up. And because of that, they just don't wind up making the intertropical convergence zone move very far north or south. But over land, it can move a lot. And that causes monsoons. Think about it. We had the intertropical convergence zone way down here in the wintertime. What happens? All the air is flowing towards it. And you wind up with cold air coming out of the central part of Asia. And have no water up here whatsoever, so you have cold, very dry. However, when the intertropical convergence zone moves back north, what happens is you pull up a lot of southerly wind in here off the Indian Ocean, the Arabian Sea, lots of moisture, and you wind up with tremendous rain. And they last for months at a time. depending on when the intertropical convergence zone moves by your area. So these are global features that impact these local area weathers. And here we've talked about the east side of the high versus the west side. Well, San Diego's on the east side. Guess what? They don't have much rain at all. Charleston's on the west side. A lot more rain. And because these circulations set up over the water, they influence the currents of the ocean. Because of the high pressure around 30 degrees north, what do you have? A North Atlantic gyre develops right there because of that high. And there's the Gulf Stream coming right up on the east coast, bringing warm water northward. Helps to keep at least my area and even further north a little bit warmer than it would normally be. And some of that warm water tends to mix it all the way over towards England. It helps Iceland actually stay a little bit warmer than it might otherwise be. So these gyres that are in the ocean, the currents that are there, look at it along the California coast. Everything's coming down from the north, down from Alaska area and such along the coast. Well, what kind of temperatures is that going to give? It's going to bring colder water in. So you wind up with cooler oceans on the west side of continents and warmer oceans on the east side of continents. Here is a monsoon that actually occurs in the United States. It occurs in the southwestern United States. Why does it develop? It develops because there's a lot of heating. There's a higher range of mountains here in Mexico. And that area really heats up in this early part of summer. When it heats up, the air begins to rise, gets less dense. You form a little low pressure down there at the surface. Aloft, the low actually becomes because it's very hot air. Pressure changes very slowly in the vertical. You actually develop high pressure aloft. And this pulls in moisture from the Gulf of Mexico and even some from the Pacific. And then it moves north and into the southwestern United States. And this pattern can consist for months at a time, bringing in lots of rain to that area. And this is some of the wettest seasons in the southern parts of Arizona and New Mexico. Rossby waves are really big waves. So let's take a look at a Rossby wave. I wanted to show you this. What is a Rossby wave? It's a very confusing concept. It can be. It is a long, if you were to average, there's here a little wave, maybe even another one down here. Put them all together. In this area is some broad area of low pressure. I would argue that it's probably the steepest in the western part of the U.S., just on the east side of the Rocky Mountains. So all these littler waves, when they come in, will tend to drop down, get the strongest in this area, and then there's high pressure to the east of that Rossby wave. So they wind up shifting up. And that is why the east coast of the United States, the last week or so, has been a little bit warmer. There's another Rossby wave, probably here towards Europe. And I'm looking at the pole right now, looking straight down. But there's about 4 to 5 Rossby waves around the world right now at this moment in time. So that's what a Rossby wave is. It has a bunch of little, what we call short waves running through it. They tend to deepen. And when you let Rossby waves, we have one towards the eastern part of the United States, we tend to get stormy. We tend to get cool. If it's in the western United States, they tend to get that. And here you can see the flow around the Earth. If it's zonal, you can still see there's little waves in it, but really most of the cold air stays to the north, most of the warm air stays to the south, and low pressure systems that run along here with little cold fronts with them and warm fronts ahead of them tend to be weaker, and they tend to move very quickly. You can have this kind of a flow pattern across the United States sometimes, and if you're a pilot, think about it. If you're going from California to New York, you may have a heck of a strong jet helping you to get there really quickly. Meridional flow, on the other hand, pulls a lot of cold air way down south. So you wind up with a very extreme temperature gradient because a lot of warm air has come up ahead of it. And this temperature gradients help to develop very strong low pressure systems This is when you have your most powerful lows, and they tend to move slower around the globe. And eventually, some of these even get cut off and they block systems. Many times when that happens, it can cause weather patterns to just stay over the same area for a long time. This is just one example where you wound up with the eastern part of the United States didn't get much rain during this summer of '93. However, in the Midwest, they kept getting thunderstorm after thunderstorm. Rivers were flooding. They just couldn't get out of tremendous amount of rainfall there. And you can see here the block pattern and precipitation. Okay, when you have a temperature contrast, we know that creates a pressure gradient. Well, where the temperature contrast is greatest, the pressure gradient is going to be the strongest, and that's where your jet streams form. So if the temperature contrast is greatest right along a front, which is where it typically is greatest, that's where your jet stream is going to form. So when you look at where your jet streams are, they typically are the dividing line between cold air to the north and warm air to the south. And the Coriolis effect impacts the winds. And you can see summertime, the jet stream moves north. Wintertime, the jet stream moves south. Interestingly, in the Rossby wave, there are little weak jet streams, jet streaks, and as part of that, these are what we call short waves because they're not a big, long wave like a Rossby wave is. And when they're moving through the flow, you find up with some winds slow down maybe and get some convergence developing, or wind speed up and you get divergence. And this is all aloft. This is around 20 to 30,000 feet aloft. Well, that impacts the surface. If we have winds diverging aloft, air's got to rush up from the surface to take their place. And if that happens, you wind up getting lower pressure at the surface. That's where lows form. So that's why you tend to see the lows on the east side of a Rossby wave and not on the west side. Tend to see high pressure here. And here you can actually see the pattern. We're going to get into a lot of depth here in the next weeks, why these lows form and what they are. Here's the jet streak, left front quadrant of a jet where the air begins to get strongest winds. There's your best divergence, and the right rear is the other area. These are the areas where they come across thunderstorms, bad weather tends to occur. El Nino is a large-scale circulation. It's an ocean and atmospheric circulation. The two work together. Currently, if we were to look at El Nino going on, I think I might have it right. Well, there's the tropics. Here's El Nino. What we do is measure sea surface temperatures at different depths and different locations. Nino region 3.4 is what they use. It's in the middle of the Pacific region. And look at how cold the temperatures are. -1 consistently almost all winter long. And that is what was required. At least 3 months of roughly around between greater than -0.5 degree. Yeah, these aren't huge temperature changes, but they're enough to influence the weather. And this is what we're dealing with right now, is that we have a La Nina. El Nino, you would have the warmer, but we don't have that going on right now at all. So, finally with this, here you can see how it changes from time to time. El Ninos tend to bring a lot of rain to California and the West Coast. They also tend to come in very quickly across and tend to create more low pressure systems as they're moving across the United States. La Ninas tend to keep the cold air to the northern part of the United States, a little warmer to the south. And guess what? This winter, we had lots of cold air up in the northern part of the United States. And while the southern part of the United States actually was a little bit warmer than normal. Ekman's spiral. This occurs along the coastlines. If you went to the Outer Banks and say you were going to go swimming there, one day the temperature might be 80 degrees. Well, the next day it could be 50 degrees. Why is that? Well, say you have a southwest wind along the coast of the United States. It begins to turn because of the Coriolis effect. The water will actually turn to the right with time. And as that happens, you wind up spinning it around so that it actually comes towards shore and pushes the low-level water upwards. So the longer a southwest wind occurs along the eastern United States, the cooler the water may become, all because of the Ekman spiral. It also occurs along the equator. And here we talk about El Nino and La Nina and how they can change the patterns of the weather around us. And then there's a North Atlantic oscillation. That right now is in a positive phase and has been for most of the winter. It really influences the eastern half of the United States. Depending on whether it's a positive or negative phase, you can bring in cold air or you can have warm air. You can bring in strong storms, you can have less storms. And it's a very difficult thing to forecast, but it tends to stay in one phase or another for several weeks at a time. Then it usually shifts. Sometimes, like this year, it's not shifting a whole lot. And here you can see some of the characteristics of it, what they before. And here's the Arctic oscillation. You hear about that. Sometimes there's a strong in the stratosphere, very low pressure typically at this time of the year. It gets extremely cold there. And when that breaks down, what happens in the Arctic oscillation is it allows that cold air to slip southward. So if that circulation is weaker, the cold air is going to begin to move further south in the United States. If it's stronger, cold air tends to stay up north near the poles. We stay a little bit warmer. And then here's two phases, and you can see the impact it has. There's Pacific phases, another decadal oscillation, the long-term phase. Madden-Julian oscillation. It's an area of thunderstorms that tend to develop over the Indian Ocean, and they traverse to the east with time. And what happens is when they really get going, they can influence the Pacific. We've talked about atmospheric rivers in the Pacific. Depending on the right phase of, if it's an enhanced rainfall phase with a lot of high moisture in the air, you can push a lot of moisture up on the Pacific in the Pineapple Express, as they call it, and a lot more moisture comes into the Pacific coast of the United States. If it's in a suppressed rainfall phase, you won't get as much. So this actually moves around the globe, and you can track these. And they can influence whether hurricanes or tropical systems develop sometimes in the summer, depending on where they are. If you actually, when you look through our Sandy discussion later on, we're going to be writing about, MJO actually impacted why Sandy developed. So just something to think about. So I hope you got a little bit out of this. I know kind of went a long way here. So let me know if you have any questions.